So, my name is Aino Kainulainen, and I work for the Helsinki Region Environmental Services Authority, so close enough, Esko. And so we are responsible for the waste management and water management of the Helsinki metropolitan area, which is Helsinki and a few neighboring municipalities. And we've been working with sludge pyrolysis for a few years now. First, just a few words about the organization. So we are, as I said, responsible for water, drinking water treatment, wastewater treatment, and then municipal waste management, which is basically can be taken in two parts. There's the bio waste management that links into sludge treatment that we're talking about today. And then there's also the other sort of more technical waste management, including the slag and ashes from waste to energy. And we also do advisory services and information production about the environment and the metropolitan area and the air quality. And there's a lot we do. The strategy of HSY is to be an enabler of clean and sustainable urban environment. And the most important part from my point of view is that we try to be a forerunner in environmental responsibility and resource efficiency in Finland. And that includes actively taking advantage of new technologies. And that's where I come in. I'm working as the research and development portfolio manager at the waste management sector of our organization. But I work closely with the wastewater management people as well. So we have joint projects, which this is one example of. The big vision that we have about resources from wastewater is that there's two parts of a bigger project. One part is the Ravida process, which is developed by HSY, and the main goal of the process is to capture phosphorus from wastewater without it entering the sludge. So the phosphorus is not precipitated in the early stages of the wastewater treatment process as it is usually done, but instead as a post-precipitation process, and thus it doesn't go into the sludge, and that's about 70% of the phosphorus, and then 30% goes into the sludge. Biologically, there's no iron in the sludge in that case, and that's where we come in and we do the pyrolysis to get rid of any pharmaceutical residues or microplastics and so on, and produce a char. But this is all still at the pilot stage, so we don't have a working Ravida process at the moment. The current project that we are in is going to scale the process up in a smaller wastewater treatment plant in Finland, because ours are quite big and we can't risk sort of trying new things because the water volume is big and we are right at the Baltic Sea, so we are very strict about our limits, and we are very sort of conservative in that case, in that sense. But we'll be scaling that up more inland with some other wastewater treatment facility soon. But today we're focusing on the pyrolysis part. Some background why we went into into sort of the project of looking into new technologies. One big issue is the windrow composting, which is the sort of normal way of treating wastewater sludge, is a lot. It consumes a lot of space, and it produces a lot of odors. And our site at the Amazon Waste Treatment or Eco Industrial Center is sort of there are two municipalities on either side, and they are both growing. So we get more and more neighbors, and when we get more and more neighbors, we get more and more complaints about smells. And we wanted to look into alternatives that would reduce the need for a space, and especially reduce the odors that come. So more sort of controlled processes for treating wastewater sludge. And we started in 2015 with a project that we gave sort of a big shout out, or try to get companies to answer us and how should we treat this stuff. And we got many answers, of which then 4 were selected for testing. And the criteria then was that it must be suited for digested and centrifuged sludge, because that was the sludge that came to the Amazon Center, and we didn't want to mess with the process at the wastewater treatment plant. They do need to digest the sludge there in order to get the energy balance of the wastewater treatment in order. And then we wanted it to have a good energy balance, the ability to destroy harmful substances, and we wanted it to have as little waste streams as possible. And with this criteria, we ended up with pyrolysis. So pyrolysis in sludge management, the high temperatures ensure the destruction of pathogens and also organic contaminants. So organic contaminants are these medical residues, fire retardants, and then microplastics. We don't have any analytical methods yet for determining if microplastics are indeed evaporated from the SludgeChar. So we can test the sludge for microplastics, but there is no analytical method at the moment to test the char. But with the temperatures that we use, I am quite confident, and so are many experts, that the microplastics will be also evaporated and then burned with the syngas. But as soon as we have a method for this, we will be using it. The remaining char is mainly composed of carbon and at the moment iron. As I said, when we get the Ravida process that I mentioned earlier, when we get that running, then we won't have that iron in there. There's also quite a lot of phosphorus and then calcium. There are still some knowledge gaps about the end product. We have been filling these gaps in the last few years. I'll show our research results soon in the next slides. But we are still working on this, and the goal of this project has been to study the properties of SludgeChar, what it is and what it can be used for. And now we are moving into pilot scale. We don't work alone. Since for the last previous years, our research partners have been Luke and Gasum. So Luke is the Natural Resource Institute of Finland, and Gasum is a biogas company that's based in Finland, but also in other Nordic countries. You might be familiar with it. And now this year and next year, we are working with the Häme Ammattikorkeakoulu, so Häme University of Applied Sciences, I think the English version is, and they are very active in biochar things and have good research there. So we're working with them for the next few years. And I'm doing a PhD on this as a side project, sort of, and thus we are getting research support from the university I'm doing the PhD in, so Aalto University chemical engineering. So 2019 we did some pyrolysis test runs at the Gasum facility. At that point they owned a small pyrolysis or sort of pilot scale pyrolysis facility in Turku. And so we tried our sludge and their sludge. There's a bit of difference between the sludges. And we dried them. There was a vacuum dryer, and we pyrolyzed them at 2 different temperatures to see if there's any differences between the temperatures. And we took samples before and after pyrolysis. So we had samples of dried sludge and then the pyrolyzed sludge that we call SludgeChar. And what we studied from them was the chemical composition. So what nutrients they had, if there was heavy metals, pH, electrical conductivity, organic contaminants. Then we wanted to look at the structure of sludge-derived biochar. As we know, wood-derived and other plant material biochar does have a sort of a very porous structure. And we were expecting this not to have as much porous structures, and we know that these structures are relevant when we use biochars in different applications. So we wanted to look in that to compare it to conventional biochars. And then we wanted to look at the sludge-derived biochar as a fertilizer. So if it isn't a sort of a proper biochar, could it be then a fertilizer? And we were also adding nitrogen to the end product because that will evaporate in the drying process. And then one interesting application for us was using it as a composting amendment. We had tried biochar earlier with good results, and we wanted to compare the SludgeChar to this conventional biochars. And then the results. As expected, non-evaporating heavy metals are concentrated into the char. I'm sorry, the table here is in Finnish, but I guess you can. Kupari is copper and lyijy is lead, and the other I think are quite sort of, you can deduct them. So these are concentrated into the char, but they do not exceed the limits of fertilizer legislation. So we were quite happy with this. We, of course, expected them to concentrate. With the new EU Fertilizer Act, copper and zinc are quite close to the limit values and exceed them at times, but so these we need to look into more closely if we want to use this as a fertilizer product. Organic contaminants, we tested for 174 different organic contaminants. So there was a long list of fire retardants and plasticizers and drugs and pharmaceuticals and hormones and so on. Most organic contaminants were eliminated or reduced very significantly. As you can see here, the BDE and the PFAS as sort of examples of that. And diclofenac is here as an example of pharmaceuticals. That's one of the most concern raising pharmaceuticals, because it is very bad for at least aquatic environments. And that we saw disappear completely, which is very, very nice. Paracetamol, for some reason, is the exception. It is increasing in concentration with this heat treatment, and we've seen this in other projects as well. One sort of educated guess I've heard is that when paracetamol degrades when people consume paracetamol and it degrades in our bodies, it comes into other products, and these products might, in the presence of this heat, then sort of turn back into paracetamol. So that's quite interesting, but fortunately that's not one of the sort of most concern-raising pharmaceuticals out there. So we are not very worried about that, but it's sort of an interesting outlier that this can happen as well. Then, as I guess you know, PAH, polyaromatic hydrocarbons, and dioxins and furans are of course also a concern, and they're more related to the process itself and not the masses or the feeds that you process. With this machinery, the PAH levels as well as dioxins and furans were below all the guide values for chars, so they were in the premium class of the European biochar certificate. Nutrients. Phosphorus concentrates into the char, so that's not, it doesn't evaporate or turn into anything else. It constitutes about 5% of the end product. And due to the iron, again, in the sludge, the phosphorus is quite low. The solubility is quite low. So this we expect to change with the possible new sludge that we're going to get in the future. At least we hope so, and this is something we're going to test soon to try to get our hands on some biologically treated or with biological phosphorus removal, some sludges that we can then pyrolyze and study. Unfortunately, this biological phosphorus removal is not very common in Finland, as it's mainly it works only in warm temperatures, so it can only be used in the summer, and it's not as secure as the removal of phosphorus with these iron substances, so chemical removal of phosphorus. So that's why it's difficult to find any sludges to study, but we have now located some, and we'll try it. Nitrogen evaporates in the drying process, but we need to catch it anyway with the scrubber, because we can't just let ammonia into the air. It's again a very smelly gas, as well as for not good for your breathing. So we are scrubbing it anyway, and we can return it to the char when we are quenching it after the process. So we get it now in a ammonium sulfate form. So we are scrubbing with sulfuric acid. We could do that probably with phosphoric acid as well. So that's something we need to see as well, if it's more interesting than the sulfuric acid. And the sorption potential was comparable to other chars, which is sort of a positive surprise for us. We are now comparing on a volumetric basis. So a liter of char, how much of nitrogen it can absorb, because Again, the iron makes SludgeChar quite heavy, and there's no sort of point in then comparing it to very light chars for sort of application wise, because the weight is going to make it look very bad, and that's why we wanted to look at volumes, so it's sort of on the same line with others. So here the other charts that we are comparing to are the first three are the Gasum 400, Gasum 500, HSO 500. These are the SludgeChars that we used. Paju is willow. Then there's chicken manure. And then the last LG85 is a commercial activated carbon. So you can see that they are quite close to the willow char and quite close actually to the activated carbon as well. Only the chicken manure here was better in all tests. Then into the structure. As we expected, the porosity of the SludgeChar is quite a lot smaller than the porosity of wood-derived biochars. So you can see in the picture there's the Lietehiili is SludgeChar, and then Pajuhiili is willow char. And you can well see the difference for yourselves there. And the surface area of chars is very much is a sort of a crucial parameter for many conventional uses of biochar. So if we're using it, especially in the composting process, where the bacteria use all these holes as their homes and grow there, then the SludgeChar is obviously in a negative disposition there. And water holding capacity is another thing. So with this low porosity, it's the water holding capacity is of course also smaller. And here in the picture, there's the pore diameter, but then there's also the picture B, and there you can see that the pores in SludgeChar were actually these sort of balls. We're thinking that this is because of the water evaporating and leaving sort of these holes. So that might be due to the drying process. It was a vacuum dryer, so it might have sort of created these small explosions of water inside it, and that's there's some ball-like structures in the char. So we'll see. I hope we can make. We now have a different drying process, and I hope I can get new pictures of similar pictures to see if that affects the structure. And then what we are doing now is looking at SludgeChar in an aerobic digestion of biowaste. So we saw that composting the materials quite tense, and it can create pockets in composting that can are sort of anaerobic, and thus this might be a better use for it. And we have done some tests, and the results this far are promising. It seems that the SludgeChar has a stabilizing effect on anaerobic digestion of biowaste, because biowaste is really nitrogen rich, and it's not an easy feed for digestion. these processes are quite prone to collapsing for different reasons. For the sort of, if you drive it too hard, it can collapse easily, and it seems that SludgeChar is actually helping the process to keep stable. And also, it does seem to have an effect on the end product. So the fertilizer that comes after the anaerobic digestion, it seems that the nitrogen in the end product is more readily available for the plants. So you can see the salad on the right there, and the third from the left is the SludgeChar version. And as you can see, the roots of the salad are quite a lot better than compared to the control with no fertilizing, and then there were sort of bio-waste digestate without the char, and then there was a commercial fertilizer as a control as well. And then another thing is stormwater treatment. There's some promising results there as well. We think that this is probably due to the iron that I have seen as a negative thing in many applications, but in this case it might be a good thing. So there, the bottles you see, D is the control, and E and F are the SludgeChar applications. So the water is quite a lot clearer after that. This is in a sand filter, so addition to a sand filter. So we'll see. These are topics that we will be looking at in this year and next year, and I hope we can publish some articles on these then. And now to the pilot facility. So in view of promising results on the chemical composition of SludgeChar, we are confident that this is a good technology for us, and we are now piloting it. So we have built a pilot plant, which is about 10% capacity of a complete plant that we would have. And what we want to do is first of all to secure the operation across the whole process, because drying of sludge is one sort of big question mark, what the best technology for that is. And then of course there are a few sludge pyrolysis plants already out there, but now with this design, we wanted to get a design that it's not screw based, but it's actually a drum reactor, because that we can scale up more easily. If you have screw reactors, you really need, the scaling up is basically just putting them next to each other, and we'd need at least I think 7 reactors to cover the need for treatment that we have. And of course, we want to also look at emission information for environmental permitting. So we are working with the permitting officials to see what the actual emissions are and what the permitting needs to be for the full-scale application. And of course, we want to also determine actual operational costs. So this is one big question mark, of course, if this is a good way of treating sludge in the future. We can't really compare it to windrow composting. I feel that windrow composting is It's still possible in some areas, but not in this area we are working with. So we need to compare it with other more sort of technically advanced technologies. And of course, sludge treatment is never a thing you can get money from. So it's gonna cost you anyway, but how much it will cost is a good question, and we want to see before we invest. It's going to be at least 10 or 20 million the investment in the full scale application. So we want to be sure before doing that. And we also want to optimize the process through adjusting operational parameters such as temperature and retention time, and feed mixing ratios. So we are using wood as a mixing material in this facility because we want to make the process energy self-sufficient. And sludge itself doesn't have much energy in it. So adding wood to the process makes the gas more energy rich, and then we can heat the dryer and the pyrolysis reactor with the gas from the pyrolysis. So it doesn't require outside heat feeding. Of course, electricity it does consume a bit. And also learning about the properties of the flue gases. So in this case, because we are pyrolyzing sludge and then burning the syngas, the burning of syngas is basically seen as waste incineration. So we need to have emission control as if we are incinerating waste, and that's of course quite strict requirements, and we are now learning about the properties of flue gases in order to see what the technology needs are for the big plant, because that's the sort of most expensive part of the plant is the emission control. And the energy balance, as I mentioned, also waste streams. So as I mentioned in the early stages of the presentation, we wanted to have as little side products or waste streams as possible. And we've tried to optimize this plant so that we don't get any tars or liquid fractions from pyrolysis. So the burning of the syngas is very close to the actual pyrolysis reactor, so that we don't condensate any tars and we burn them alongside with the syngas. So hopefully we only get a char and a gas, and at this far it seems so, but we've only been running it for a few days, so we'll see what we get. Here's a closer look on the plant before we watch the video. So it starts with the numbers 1 and 4, which are bunkers. 1 for sludge and 4 for the wood chips. And then they are mixed and conveyed to the number 6 there, the big blue thing, which is the belt dryer. And they slowly move through the belt dryer, and once they're dry, they go into a buffer hopper, or sort of a buffer silo there, number 9, and from there to the actual pyrolysis reactor, which is number 11 there. And there the syngas is then burned, and there's a heating oil system that then captures the heat from the incineration of the gas and transfers that to the drying process. And then in the end, the char is quenched with water or the ammonium sulfate that we get from cleaning the air of the drying process, and then stored outside in a storage pit. So the cleaning of the drying air is through a acid scrubber, as I said, and after the acid scrubber, we also have a biological filter to take care of the other sort of smelly substances besides ammonia. And we should get quite clean air in the end. And the cleaning system for the flue gas from the pyrolysis and the incineration of the syngas is then a dust filter to get rid of any for example, mercury and other sort of harmful substances that might be in the flue gas. And these are hazardous waste, and we do have a hazardous waste landfill at the site, so that's not a problem for us. Hopefully the amount is very little, but we'll see when we run it for a while how much of this waste we get. Yeah, so here's some pictures of the facility when it was built. So that's the round thing is the pyrolysis reactor. It was we commissioned the plant from Tecam Soluciones Medio Ambientales, which is a Spanish company. And that's a rotary kiln, as I said. Here's my contact details and the site that is currently only in Finnish, but we will be making translations of the website, so soon there will be English material in there as well. And you are always welcome to contact me. Of course, you're welcome to ask anything now, but also to contact me via phone. You need the international 358 before the number if you're calling from abroad. And LinkedIn and Twitter are also options. I'll stop sharing so Esko can then show us the video and then we can talk. Yeah.
Household side streams are resources we cannot afford to waste. We at HSY are developing innovative methods for utilizing the nutrients and carbon from municipal wastewater in order to enhance circular economy. The pyrolysis of sewage sludge is an important strategic project for HSY. Together with Ravida technology, HSY has formed a concept where nutrients and carbon from wastewater can be recycled more efficiently. Ravida recovers nutrients directly from wastewater. The remaining sludge can then be pyrolyzed. We have built a pilot plant at the Ämmässuo Eco-Industrial Center to test the pyrolysis of municipal wastewater sludge. With this method, dried sludge is treated in a low oxygen environment at high temperatures. The pilot plant is used for optimizing the process, its energy balance, and the production of a high quality end product. First, the sludge and wood are mixed together. Wood is added to the process to make it energy self-sufficient. The mixture is dried with a belt dryer. The exhaust air from drying is led to an acid scrubber to capture ammonia and then to a biofilter to remove odors. The dried mixture is led into the pyrolysis reactor where it's treated in a low oxygen environment at 450 to 650 degrees Celsius. The pyrolysis gas formed in the process is burned and the resulting heat is used in the pyrolysis and drying processes. The flue gases are treated according to official requirements. After pyrolysis, the end product, we call SludgeChar, is quenched with water or ammonium sulfate to return the previously evaporated nitrogen into the end product. The char can then be used as an amendment in biowaste treatment, directly as a soil conditioner or as a filtering medium. Char from pyrolysis is chemically very stable. If used in soil conditioning, it will not be released back into the atmosphere and thus it will not contribute to climate change. We work together with many different research organizations. We studied properties of SludgeChar and possible new applications for its use. Cooperation enables us to be forerunners in our field.
Great. I guess it's now time for questions. Julia, would you like to, or do you want to continue, Aino, still, or is it time for a
No,
question?
I don't need to continue. I saw that there are 2 questions in the Q&A section. Should I start with these?
I think
Yes,
Julia can maybe ask you the questions so we can
Yeah.
get them on the recording as well.
yes, sure. Yeah, we don't have that many for the moment, so we can tackle them. But first of all, thank you very much, Aino, for the very interesting presentation. It was very good to hear all of the research you are doing on the SludgeChar. And so perhaps we start with the first question, which mentions the most abundant metals that you detected in the SludgeChar, and the question is if they are in a mobile form or if you tested, if you measured which form they are in, and if they're actually, I guess, in an available form.
Yeah, we don't actually know that yet. So these results are just the total of copper and the total of zinc and so on. We will be looking into that if they are sort of available, or if they can get out of there into water and so on. So that's something we are still looking into. But those results were anyway from sort of pure sludge, and now that we are adding wood to get the energy balance, I think this will also take care of the limit, because they are so close to the limit values that we won't go over them with the end product that has about 20% or so of wood.
Yes. Okay. There is a second question about the operational costs, if you have any forecast or guess about that.
Yeah, our best guess at the moment would be around 80 euros per ton. So that's double of the cost of windrow composting. But as I said, we can't really compare it to windrow composting. That's because that's not going to be an option for us for at least a long-term option, I think. It is comparable to incineration, which is actually, if you want to recover phosphorus after incineration, that's going to be more costly than the pyrolysis. So that's a good thing. We don't want to do the incineration because that would release all the carbon dioxide into the atmosphere. And with pyrolysis, we actually can control or get some of the carbon stored for a very long time instead of getting it into the atmosphere. So that's one of the main drivers for us if we are comparing to sludge incineration, which is quite common in Central Europe nowadays.
Yes. Yes, and I was wondering then, the dimension of the plant is meant to handle all of the sludge that you need to process, right? So your plan is to, with this plant, to completely stop with windrow composting. Is that correct?
Well, this plant is well, this is 10% of the full-scale plant, and the full-scale plant that we are planning, that takes care of about half of the total sludge that we have in the whole area. So we have 2 facilities that handle sludge, and this one in Espoo is in the sort of a more central location than the other one, which is way in the sort of east part of our area, and that's sort of still woodlands, and will be this sort of looked into after we make this make the decision with the sort of western and more urban area that we are working with. So we'll do it in parts.
Steps.
So this will the full scale will cover about half, and still half will be windrow composted, and we'll see what we do with that after we decide what we do with this one.
Okay. There is another question about the cost, because you mentioned the cost of the plant between 10 and 20 million. I guess you meant euros. Okay.
Yeah.
Then we have a question from Preet that maybe you can also read in the chat. So the SludgeChar has 25% of carbon, and it was mentioned that it is highly stable. What is the evidence, like for how long the mean residence time of the carbon, or how much is still left after 100 years? Have you done any incubation or modeling for the carbon stability?
Not yet. We hope to be able to do something. So the mention of stable carbon is my best guess at the moment, and we will do some testing with this new project now to see if it actually is very stable. But it is very thoroughly charred, so in that sense it should be as stable as biochar itself.
Yes. We have a question about your experiment with anaerobic digestion, which I'm actually also very curious about. And the question is, what kind of bio-waste are you using in the anaerobic digestion, where you had the good stabilizing effect? And I would also add from my side, what kind of experiments are you doing, like with batch digestion or?
We are doing continuous digestion we had a 5-liter reactors and then 3-liter reactors, both used in this. So it is continuous. It's been going on. The first we ran was for I think 5 months. So we did get because we started gradually feeding the SludgeChar into the reactor, so we wanted to make a long run out of it so that we could get a concentration of the SludgeChar into the reactor in this sort of to model the continuous process. And the bio-waste we are using is as close to municipal bio-waste that we can get. So our bio-waste comes from the inhabitants of the areas. So not very sort of homogeneous industrial bio-waste, but just normal municipal bio-waste from people's kitchens.
Nice. Yeah, we have many questions. I think you already mentioned perhaps about the capacity of the plants that you are, so the tons per hour that the plants can process, and also what kind of pyrolysis reactor you're using. I think you mentioned a screw reactor, but perhaps you can.
Yeah, it's I mentioned a screw reactor as it is not a screw reactor. It's a drum reactor, so rotating kiln reactor. So it's a big sort of kiln that rotates slowly, and it's heated from the core.
Yeah, and the capacity per, like in kilos or tons per hour.
I need to look into the kilos or tons per hour. I only remember the tons per year. So that's 3,000 tons per year of digested and centrifuge sludge. So a sludge with a moisture of 70%. So dry matter, 30% of dry matter.
Okay, we have also another question on the process, asking how much biochar is produced compared to what's the yield of biochar compared to the raw material?
Yeah, so we have 70% of moisture in the feed that goes away. We have 30% left of the stuff when we take it into the pyrolysis reactor, and we are still there, of course, losing a bit of the stuff that evaporates, and we think that we get about from the 3,000 tons per year, we get about 600 tons of the end product, I would guess.
I don't know if the other panelists have any question. I would have one, or yeah, also attendees, please feel free to write in the chat. We still have a few minutes. But I was curious about the ammonia recovery system, and you mentioned that you want or you plan to recirculate this to the char.
Yeah.
So in practice, how would that work? Would you impregnate the char with the recycled ammonium sulfate, or?
Yeah, we do that in the quenching part. So we need to use some liquid to quench the char when it comes out of the pyrolysis reactor, because if we leave it sort of hot and dry, it will react with oxygen and burn. So we already have a sort of a moisturing system there to quench the char, and we can use either water or the ammonium sulfate. And we've been trying both, I guess, now, and it seems to work. It does take in the ammonium sulfate as well, but we don't have any lab results yet of the fate of the nitrogen, if it actually can be found in the end products. And so that's something we'll know later in the spring.
Yeah, but that sounds like a very interesting solution, because yeah, it is of course the nitrogen in the char itself, it's quite low after the pyrolysis process. And I was also wondering, so you're also testing the char as a composting additive. You do not have any publication out yet on the results about that?
No, we don't have any publication, unfortunately, out. We did some tests, but there was a lot of variation between the I had 16 reactors, sort of these small composting where you compost your green wastes outside. So there was some trend, but I didn't get a sort of a good, reliable results that could be published as sort of a scientific with the scientific certainty, unfortunately. But what we got was that it did control a bit of the ammonia coming from the composting process. So it did limit the ammonia emissions from composting, but some of the batches that I had with SludgeChar did also produce a bit more methane. So there were sort of pockets of anaerobic digestion in the composting reactors. These were reactors that were very hard to mix. I tried to mix them the best I could, but in an industrial process that we have better mixing, and we have a forced aeration, which is not the case in these sort of reactors that we had in the composting test. So I think the problems could be solved when we have a forced aeration and a good sort of industrial composting process. But unfortunately, the results weren't certain enough to be sort of a scientific publication.
Okay, but that's interesting, especially if you plan to keep the windrow composting in parallel with the pyrolysis plants. Perhaps it could be a good synergy. We have a couple more questions, and Rune is asking, what is the operation temperature you decided for the pyrolysis? So what's the maximum temperature in the pyrolysis plant?
We are now, this plant is made with sort of a large range, so we can still test the lowest is 450 that we're going to use, and the highest is 650, I think. So we'll be doing the first runs we do with this when we get it properly well running is still in the commissioning phase. So we are now running it with the company that provided it, and when we are certain that it runs properly and everything is okay, we start the actual piloting phase. And the first thing we do with the piloting phase is we try, I think, 4 different temperatures with each of them 4 different retention times, and we get then results of how the retention time and temperature affects the end product. And then we choose, with the knowledge of the end product and with the knowledge that we get from about the energy balance and so on, then we choose sort of the best temperature we want to run the application with for a longer period.
I think we have time for one final question that we got about the policy side. So what licensing, approval, or which processes does the product have, and what kind of use when licensing is needed?
Yeah, the licensing situation is so at the moment that we can use the SludgeChar in bio-waste treatment, as it is still sort of, it's considered a waste at the moment, so there's no end of waste status yet, but we can use it in the bio-waste treatment, anaerobic or composting, and then it ends up in the soil products that we have. But when we know better what kind of use we want to license it for, we will start licensing processes, and reach will be needed if we want to make a product out of it itself. If we want that the SludgeChar is a product in itself, then it needs a reach status as well, and also we need to find out if we want to sell it as a soil amendment or as a filtering medium or whatever the end use as a fertilizer. We'll need to figure that out. There's a sort of a problem or a hindrance at the moment is that the EU legislation for fertilizers is in the works as we speak. So we don't yet know what the new legislation concerning fertilizers is going to be. So we are sort of unaware of the requirements at the moment, but we'll follow the legislation and talk with the authorities.
It's an ongoing process right now.
Yeah.
So it's 10 a.m. So we are out of time. So if you have any other question for Aino, you can contact her.
Yes, please do.
I thank you very much, Aino, for the very interesting webinar once again. And yeah.